We are going to be talking about how changing variables affect gases. So specifically, we're going to be talking about the behavior of gases in a fixed container. So we're going to isolate the gas in the container. The gas itself is not rigid. It doesn't take on a fixed shape like a solid would, and there's no fixed volume like a liquid or a solid. So the gas molecules just kind of fly around in the container, and we're going to figure out how pressure, temperature, volume, and quantity affect those gases within the container. First of all, we need to talk about what's called the kinetic molecular theory. So the kinetic molecular theory, or KMT, determines the behavior of gases, and there's 5 main principles. The first principle, a gas consists of small particles, which could be molecules or atoms, and they move randomly and they move with rapid velocity. The second principle is that there's minimal attraction between the gas molecules. If you increase the attraction between molecules, it would tend to change the state of matter. So there's no or minimal attraction between the molecules. The third principle, a gas will fill up any space it is confined in, but the actual gas molecules are really small. So there's a lot of empty space between those molecules, even though they're filling up a container, which means that they can be easily compressed. The fourth principle, kinetic energy, which is just the energy of movement, is proportional to the Kelvin scale. So temperature, which will be measured in Kelvin, increases, and so does the motion of the particles. So increased temperature, increased motion, which is kinetic energy. The fifth principle is that gases are in constant, rapid, random motion. They're always moving, and there's no set path to the gas molecules. So the first variable I want to talk about is temperature. So there are 3 ways to measure temperature: Fahrenheit, Celsius, and Kelvin. We're going to be using Kelvin, and the reason why is because Kelvin scale is based on the idea that molecules eventually cease all motion if you drop the temperature down low enough. What is the value corresponding to that lack of motion? That's where the Kelvin scale comes in and says, well, that value has to be 0. And so they set the baseline saying that if there's absolutely no motion in particles, we'll call that 0 Kelvin. Whereas Celsius is based on specifically water, the boiling point and melting point of water, which is 0 and 100 degrees Celsius. So that's the foundation for the Celsius scale. And then Fahrenheit. Fahrenheit's a really interesting scale. We'll read about that more. I don't really want to talk about it right now. So Kelvin is really the most accurate temperature measure. Temperature is just a measure of the kinetic energy in the gas. So how much energy do these gas molecules have? So here I have 2 conversions, one from Celsius to Kelvin, which is a fairly simple conversion, and one from Fahrenheit to Kelvin. We're going to completely avoid the Fahrenheit scale. The only reason I put it on here was because we in this country think in terms of Fahrenheit, and sometimes it's nice to be able to convert so you know what the numbers actually mean. But we're really going to stay away from Fahrenheit. So let's just say that Kelvin equals the degrees Celsius plus 273. The next variable we're going to talk about is pressure. Pressure is measured in what's called an atmosphere, or ATM. So pressure measures the exerted force on the container when those gas molecules collide with the walls of the container. So every single time a gas molecule collides with the wall of a container, it basically hits the wall, and that collision is measured as pressure, which is the force of the collision. So we measure in atmospheres. There are quite a few different ways to measure pressure. I'm going to try to stick in atmospheres. And what 1 atmosphere equals is the pressure exerted by the entire atmosphere at sea level. So the atmosphere is composed of nitrogen, oxygen, carbon dioxide, a bunch of water vapor, different gases. All of those gases exert pressure. So we're saying at sea level it's 1 ATM, and that changes with altitude. The American equivalent, just to give you context, to the atmosphere is pounds per square inch. So if you've got a bicycle, If you look at your tires, it measures in PSIs, or pounds per square inch, and the conversion for that is 1 atmosphere equals 14.7 pounds per square inch. I've got a couple other conversions here. So you can measure pressure in all of these different ways. There's the atmosphere, there's millimeters of mercury, the torr, inches of mercury, pounds per square inch, Pascal, and kilopascal. So please make sure to write down these conversions and their abbreviations because we're probably going to use all of them. In addition, on the right-hand side, there's an altitude and atmospheric pressure. So at sea level, the altitude is 0. And this is showing in millimeters mercury. It's 760, which is equivalent to 1 atmosphere. So then you slowly increase in altitude up to Mount Everest, which is 9.3 kilometers. And the atmosphere decreases to 270 millimeters mercury. So as you increase altitude, you decrease in atmospheric pressure. There's just less gas in the atmosphere up at the top of Mount Everest than there is at sea level. Volume is fairly simple. We've been talking about volume. It's how much space the gas occupies. You can measure in milliliters, liters, or centimeters cubed. And then the quantity of the gas present also matters. So the quantity of the gas present is N, and what it really is measuring is the amount of moles in a substance. That's kind of a funny chemistry word. So the amount of moles, I put some conversions here for you. So the amount of moles can be converted into grams. So how many grams does a substance have inside of it? So the first conversion is that 1 mole equals 6.022 times 10 to the 23rd exponentially atoms. This is also called Avogadro's number. So that doesn't really mean anything to us right now. But if I have 1 mole, this is another relationship, if I have 1 mole of a substance or an element, that's also equal to the mass of that element. So let's go to periodic table and show you what that means. So for helium, let's talk about the gases. So on the right-hand side, there's helium. This number down here, 4.002602, that's how much helium weighs, or the mass of helium. So if I have 1 mole of helium, I have 4 grams of helium. Another gaseous element is neon. So it's 20.1797. So if I have 1 mole of neon, I have 20.1797 grams of neon. So on and so forth. So that number on the periodic table tells you the mass, and you know that it's equivalent to 1 mole. And then lastly, 1 mole is also equal to a volume. It's equal to 22.4 liters at STP. I'm going to talk about STP later, so let's just let that sit. So then let's put it all together in an example. If I have 1 mole of helium gas, that means I have 4 grams of helium according to the periodic table, which means 4 grams of helium contains 6.022 times 10 to the 23rd atoms, which is a lot of atoms, and would take up 22.4 liters of space. So you can use the mole as an equivalency to determine how much space it'll take up in liters and how many atoms it has based on Avogadro's number. So these are the gas laws that we're going to be talking about: Boyle's law, Gay-Lussac's law, Charles' law, Avogadro's law, based on the Avogadro's number, and then the combined gas law. So Boyle's law is the proportionality is equal to pressure times volume, which is an inverse proportional relationship. As one variable goes up, the other goes down. Gay-Lussac's law, Charles' law, and Avogadro's law are all directly proportional. So for Gay-Lussac's, proportionality states that pressure and temperature both go up together or both go down together. So K equals pressure divided by temperature. Charles' law, volume divided by temperature. And then Avogadro's law is volume divided by that letter N, which is the number of moles, or the quantity of the substance. The combined gas law, proportionally, pressure and volume is divided by temperature. So pressure and volume are directly proportional to temperature, while pressure and volume are inversely proportional to each other. So you combine all three, the Boyle's law, the Gay-Lussac's law, and the Charles law together to get a combined gas law.